the screen. Can you see full screen?
Not yet.
We can now. Yeah.
Yep. Okay. So this is actually going to be relatively short because we're fairly early into the thinking process around UKSM2. So I've just put together a few thoughts, and then Jane will give a bit more on timelines and procedures. I thought I'd start by going back to UKSM1 and just remind us what we have, because we have something to step from, and I've put in references there for the various developments. So just to remind you, UKSM1 is built on a physical core, GC 3.1. It says on the bottom it's N96, L85 in the atmosphere, 1 degree in the ocean, L75 in the ocean. And then we had all these various components that we couple into the physical model. The terrestrial carbon cycle, nitrogen limitation was something new in that. Ocean biogeochemistry, which is the Medusa 2 model, is very important for carbon uptake. Then we had the GLOMAP-aerosol scheme. In particular, we coupled it to prognostic DMS and primary marine organics. And we couple on land to the dust produced by JULES and TRIFID. So one of the things we tried to do in UKSM1 was to have as many what I would call prognostic interactive couplings as possible. Viewing the physical model HADGEM3 as a safe bet. So the Earth system model allowed us to look at lots of sort of Earth system and climate Earth system interactions. Then the chemistry, we had the UKCA Stratosphere-Troposphere chemistry, isoprene chemistry, BVO emissions, and we had ice sheets, coupled interactive Antarctica and Greenland ice sheets. Although they did not get into the standard UKSM release, they came into a particular release. And I mentioned the resolution already. And then in the couplings, as I say, we tried to go for prognostic coupling wherever we could. That's risky to do it, but it allows you to look at feedbacks. So I've just listed some of the couplings, or this is actually, I think this is a text that Alistair Seller put together, where we had couplings between the ocean and the atmosphere. You can read them there, between the atmosphere and the land, between the chemistry and the physical processes, between the chemistry and aerosol, and between the ice sheets and the ocean and ice sheets and land. We probably had more couplings than one sort of written there. But as I say, we tried to make the couplings prognostic, so not relying on observational fields, so that we could say something about the future. And we tried to make them as interactive as possible. Okay, so just stepping to UKSM2, this is one slide, and this is not a definitive list. This is a list that was knocking around a couple of months ago of things that we felt were primarily where we thought UKSM2 was likely to be going. So first, say it will be built on HADGEM3, GC5. Jane's got a bit more about that timeline. We might get an early look at GC5 early in 2022, but mid 2022 is probably when there'll be a relatively mature but not frozen version for us to work with. We're aiming to have an operational or science ready UKSM2 by the end of 2024. So you can see there's a window of around about 2.5 years. Okay, some of the target developments at that time, we've kind of taken the decision that the workhorse will stay at the same resolution, N96 in the atmosphere, L85, Orca-1 in the ocean, L75. We toyed with the idea of particularly increasing the ocean resolution, but the performance of the 1/4 degree ocean, particularly in the Southern Ocean, is poorer than the 1 degree ocean. So the benefits you get in other parts of the world, and you do get some in the North Atlantic and in upwelling regions of the subtropical oceans, they didn't really outweigh the detriment in the Southern Ocean and, of course, the increased cost. So we stayed at Orca-1, and equally, we toyed with the idea of maybe going to N216, but again, the improvements in, let's say, climate related to Earth system were not sufficient to warrant the increased cost, which is significant at N216. So you would be cutting down the number of ensemble members you could do, you'd be increasing significantly the time for simulations to be produced. And we just felt that we couldn't develop and utilize a model for the things we wanted to unless we stayed at this resolution. That doesn't mean we won't try and have an exploratory or configuration at a higher resolution. Ideally, I think we'll try and use the hybrid approach that Mark Stringer has been working on, that is now, I would say, coming close to being fully usable. If we can't, then we'll have a higher resolution full model, but the high resolution full model will be extremely expensive if it's N216 or a quarter. So it's likely we try and have something hybrid N216 with N96 for the chemistry and potentially for the aerosol as well. But that would not be the workhouse model. So one of the things that we're keen on is to have a version that runs. So we have a version already that runs with emissions of CO2. Gerd, Fiona, and others have extended that, so it now runs with emissions of methane. And we would like to have emissions and deposition of all or part of the nitrogen cycle. So the ability to run with emissions and have, therefore, free running feedbacks for carbon, methane, and potentially large components of the nitrogen cycle is something we'd like. And I think that's a fairly high level, or a primary development we'd like to realize. We also want to make the Greenland and Antarctic ice sheet models standard now, so to interact with the model for more fully. They're particularly important for sea level. Wildfires is something that's been fairly extensively developed between the Met Office and people in the core group. And I think we're in a good position to have wildfires coupled to terrestrial carbon cycle and atmospheric composition in UKSM2. Then on land, one thing that's been developed is thermal acclimation of plant photosynthesis. So photosynthesis is dependent on temperature, but and has a sort of plateau maximum efficiency at a certain temperature. But as plants get used to a different temperature or thermal regime, the photosynthetic balance can change. So we're trying to introduce that. The Met Office in particular are working on some improved representation of human land use, which is important for things like land use mitigation. And then coming more to the order of today, nitrate aerosol is something that we would like to implement. Improvements to stratospheric ozone, I believe, are already on the table. Having dust treated by the modal scheme would be nice. There's a question mark there because we don't know if it's doable at the moment, but it would be nice. And then potentially some of the things we hear about today are potentially in bold, because what we hear, just because we hear about everything doesn't mean it will get in. And we will try and develop a computationally fast version as well. So we have a fast version of UKSM1, but we've shelved that now, and we'll build it off this 1.1 configuration that we're about to release. And by fast, we're running at an N48 in the atmosphere, and at the moment L38 with a lower top. So the stratosphere is poorly resolved in the fast model, and that may not be popular to some chemists, but it's the only way we can get to what we really think is a fast version. Okay, so just some words on timings and things before Jane talks. So as I said, we aim to have something functioning by the end of 2024. That's to fit with what we assume is a CMIP7 schedule. We don't really know if there'll be a CMIP7 yet, or on what time scale or what configuration it will take, nor what level of involvement we in the UK will have in it. But we're assuming there'll be something analogous to CMIP6, and that it will be at least beginning to hit the tracks around 2025. Okay, so we're continuing to develop a model where I think we want to have this maximal prognostic interactive coupling so that we can investigate our system feedbacks. So that's one aim we'll try and keep. Let's say the model will be developed on GC5, and GC5 would therefore viewed as a safe option that wouldn't have all these prognostic couplings. Would have some, but nowhere near the same amount. UKSM2 should be usable for students and researchers for their own work, so we'll continue to make sure it's supported. It's worth noting it almost certainly will be the final UM-based UKSM version. Ones after this will be based on the new ELFRIC code, so structured for different computational architectures, really. And then myself and Jane, we've been interacting quite a bit with the GC5 development team and something called a historical PEG at the Met Office, which has been put together to try and ensure that GC5 will have an acceptable historical performance. And that interaction is to try and avoid some of the problems last time, which have put us discovering things like poor historical performance or high climate sensitivity late in the day. So not all of you may know, but we developed GC 3.1 and GA 7.1 because the original model intended for UKSM 1 GA7/GC3 had too poor historical performance. So we spent a fair amount of time doing that. And you may also not be aware that this high climate sensitivity of the model was in fact even higher originally. until some problems were discovered. So we want to try and avoid those problems this time around by getting early information. So please note, while we're starting this time from an existing model, UKESM 1 or 1.1, which is about to be released, and more knowledge of what to do, we have less time. We have 2.5 years as opposed to maybe 4 or 5 years less time. We also probably have less people in the core team available to do model development. And that's the nature of the way the funding is both in NERC and the Met Office now, that more and more we're being pushed to do science with existing models. So it's hard to get funding to do model development. So there will be less people available. We learned in UKESM 1 probably a bit too late in the day that we can't cope with lots and lots of new developments. We need sort of a group developments to be grouped into let's say a package together. And I think we need to be hard on deadlines, or harder than we were last time. So we can't afford to have things coming late and being disparate and spread over lots of different testing branches, etc. So the bottom line, I think, is being early and being well tested increases the chance of making it into UKESM 2. And the last, we're about to release 1.1, and it is quite a good model, I think. So we have a pretty good backup option. We don't want to use that backup option, but it's there should things go pie-shaped. So that is all I've got to say, and I was going to hand over to Jane now.
Okay, good morning, everybody. So yeah, just following on from Colin's talk, really, this is a little bit more on a little bit more on timelines, testing and configurations and that kind of thing. So a little bit more about the practicalities of if you are developing a science change and are keen to see it implemented potentially in a UKESM configuration, really kind of how to go about it. This here just really outlines the current model development timeline within the Met Office. This hopefully you can see my cursor, but this kind of Gantt chart on the left hand side here, but really just focus on the GC5 development timeline here in the red box is what I'm really highlighting. Again, just echoing what Colin already mentioned, in that we're hoping to build UKESM 2 on top of GC5 that is currently under development, and we do hope to have, I would hope to have an early sight of some kind of near final configuration, kind of really early 2022, but as Colin says, that could be early to mid 2022. And that wouldn't be a frozen configuration. That would be, well, that wouldn't be the release configuration. It would hopefully be frozen or very near frozen. And at that point, in currently early to mid 2022, we'd really begin, hitting the ground running in terms of developing and beginning the development of UKESM 2. And I do say hitting the ground running in that, as Colin mentioned again, the aim is to have something ready by the end of 2024. So that does only give us 2.5 years to develop this quite hefty configuration, really. So that timeline to me is very, very short. I'm very acutely aware of that kind of very short timeline relative to what we had for UKESM 1. So that's the first thing really for everyone to bear in mind in terms of really having science ready at this early stage, so that we really can start building in the science in 2022 and not leaving things late in the day, because as Colin says, that is really going to be too late, and they're already quite outside of UKCA. There are other large science changes that we are also trying to get in, and that puts us under a lot of pressure. So yeah, being ready early is the key message here, and being aware of the much tighter timeline, I think, relative to UKESM 1 is the message in terms of timelines. I have put all this is all of this information is on the UKESM track pages. I've put up the web links here. Do just get in touch with me, of course, if you have any questions. Moving on to the testing procedures. So this is really very similar to how they do it in the GC, the GA development. So it's it's very much analogous to that procedure. The key message I want to make here is that it is not just about lodging code. So you can see here on the right hand side, I have the code lodging procedure, and that's kind of dealt with separately by the UM or JULES ticketing system. What we would require in the UKESM core group is that yes, your code is lodged, that is essential, and that it's science reviewed. So as you see, this feeds into to our testing procedure here on the left hand side. But really what I'd like people to do is, if they're interested in implementing a change, is of course first contacting us. So drop me an email and let me know what you want to do. But a key part of that is opening a UKESM ticket. So this is not a code lodging ticket, it's a science ticket. So it's where you come and you test your science in a recommended UKESM configuration, and you thoroughly document the impact that your science change is having on the UKESM model. And so, you know, you could so you basically own this ticket. You would, you know, probably include relevant people in the core group CC'd on that ticket. In particular, I would be included on that ticket. And you would document, you know, in terms of sensitivity tests.
Sorry,
would
Jane.
be just, yep.
We
Yes.
lost you for a couple of seconds just now.
Oh,
we were
sorry.
talking about the ticket details.
Okay, sorry. I think my internet connection is comes and goes at times. So yeah, I think basically just thoroughly documenting the ticket, running the appropriate sensitivity tests, documenting in the ticket details page how to implement your change. So that'll be how to switch it on in a row suite, for instance, or if there is a branch. Ideally, we don't want branches, but if there is a branch, that should be thoroughly documented as well. In terms of standard tests, I will now go into detail in terms of the different types of tests, but again, that will be your best again to contact the core group, and we will advise you on what the appropriate test is. Currently, the tests are based on UKESM 1, and we'll soon have UKESM 1.1 tests, hopefully come April 2021, so next month. We'd hopefully have UKESM 1.1 tests that you can then develop and evaluate your science changes on. Again, obviously, us being a fully coupled model, we obviously maintain both atmosphere only, so the AMIP configuration as well as coupled configurations. I imagine for a lot of the UKCA changes, AMIP tests will be sufficient, but again, that will be very much dependent on the science change. So again, it's just worth having that discussion with us. Again, this is all documented. We have a guidance document that has recently been updated, so that's all there on the UKESM track. And again, just drop me a line if you have any questions. So just a final point really on these configurations. So for the science tests, and I've clearly delineated here between the science tests and the code development tests. Luke will talk more about the code development tests later in the meeting. But for the science tests, these will be based on UKESM jobs. And you know, really what we want is a clean test of your science change on UKESM. So you want to be able to document and basically tell us why we should be implementing your science change. Is it doing as you expect? And clearly documenting the results in terms of standard tests, and a standard evaluation should be run on those tests as well. So as I said, at the moment, there is, again, a link here to the UKESM 1 standard test jobs. A lot of these, in terms of at the different versions, are internal suites on the Met Office HPC, but UKESM 1 and UKESM 1.1, UKESM 1 is already available on Archer 2, and UKESM 1.1 we will be porting next month. So you will have configurations available on Archer for testing as well. It's worth noting here that in terms of the science tests, you don't necessarily have to be testing at the latest version. Yes, that's what you'll need to do in terms of code development, but in terms of a science test, if you were testing something now, I think that will be okay. But again, it's worth just chatting to us, and we can discuss what the requirements are in each case. But really, science test is just a very clean test of what is the impact of your science change. The other main aim is getting your code lodged, so when we come to implement it into our prototype configurations, we're not working with branches. So that's a key message as well. So over the next year, in the run up to 2022, the aim should be getting your science tested, code lodged, so that we're in a position just to really start flicking the switches and turning things on and testing them in our prototype configurations. In terms of the code development, obviously that is a parallel different procedure, and that's the key message I want to get across. Just by getting your code lodged does not mean it's going to get into a UKESM configuration. So that's a separate procedure. It's a very important procedure, which Luke will talk about, but in the core, and people in the core group can of course help and advise on this capacity as well. But really what we're interested in is already you come to us with the code ideally lodged, and then we proceed on that science testing side. So hopefully that is clear. And I think that's all I have. So if you do have any questions, fire away.
So now we're going to move over to the Science Advances talks. And
okay. So yeah, thanks for everyone for asking. I'm just going to talk about very briefly about some of the work I've been involved with for a while now, since my PhD really, on sort of cloud water pH and sulphate aerosol formation. So I probably don't need to spend too much time on this, but why is it important? So obviously sulphate is oxidized by two sort of main ways: within the gas phase with reaction with OH, but also in the aqueous phase, dissolved in cloud water, by reaction with hydrogen peroxide and ozone. And so looking at this, it was really looking at the ozone reaction and some testing we were doing as part of my PhD, an earlier version of UKCA and a couple to HAGEM. And we, looking at the ozone reaction is very sensitive to pH, and we wondered if this could have an important impact on more sulphate aerosol formation, its evaluation, and some of the biases that were found in some of the versions of UKCA. And so this mainly came up from some of the work at Leeds, looking at perturbed parameter ensembles, where cloud water pH and its influence on more CCN and aerosol formation then was found to be one of the most uncertain parameter, well, one of the largest contributors to the uncertainty in CCN formation. So it was a particular forward, and we didn't really have any guide on what to do with it really. So, and it's a very important process. It counts a lot of sulphate aerosol formation and maybe isn't well thought of sometimes. But the major issue we found, obviously, especially in UKSA or earlier versions of the offline aerosol model, they tend to use a globally fixed value of cloud water pH to use in these reactions and for the dissolving of SO2, and also then it's important for wet deposition as well of things. So it has an important issue, important contribution to a lot of things, but has this sort of universal fixed value of pH of 5. So just a bit more information on that for hopefully. So this is a quick to show the reaction rate at different levels of pH for sulfur for oxidation. And you can see the reaction with hydrogen peroxide is very flat and sort of pH independent, whereas this solid line with ozone here is the reaction and very pH dependent. So this is why it's so sensitive and it becomes important at certain values of pH in certain places of the world. But what was more important when we were looking into this work is obviously how spatially and temporally variable pH could be. So this is rainwater pH used as a proxy for cloud water pH, because observations and understanding of cloud water pH is a lot less than this. And so this is a spatial map from a study reproduced, and you can really show that pH is very variable over the world. You've got very high values near dust and more mineral sources, and low values more sort of polluted acidic sources. So high areas of SO2 pollution in different regions of the world. So again, using a global value of pH 5 for everywhere in this world clearly does not capture the intricacies of this different variability in pH. And equally, over time, especially rainwater pH over Europe, you've seen this gradual trend in observations. This is now, so these are lots of different sites across Europe which measured rainwater pH since the late 1970s, mainly for acid rain issues. And you can see there's this gradual marching increase as sulfur dioxide is cleaned up, you get this rise in pH. So again, this is not captured at all using a global value of pH for the whole time period as well. So these are two things in some of my early work. I was looking, what was the impact of these different pH changes, which we don't account for, on sulfur aerosol formation. So this led to a work that came out of my PhD. I've started it and then finished it off later. And just to quickly summarize, this is evaluating this version of the model, surface sulfate concentrations, and the colors represent here different values of pH used in the model. And then we've got the seasonal representation. So you can see certain seasons pH is not very influenced, but here, particularly in the wintertime, over the USA, which is this improve, Europe, which is EMIP, and some East Asian networks, and then altogether, you can see pH of 4.5 has a very large bias of sulfate formation. pH 5, which is closer to the model, and pH 5.5, we still have a large bias. But as you ramp up the pH, in a really dirty sort of way, you get an improvement in pH over the wintertime sulfate bias over Europe. And then also what we took through this of how this affects aerosol radiative forcing over the recent decades. So just again to quickly summarize, this is different values of pH in the 1970 period, and this is different values of pH in the 2009-10. And this is tried to look at, if you have a trend in pH as well, how that affects recent aerosol rated forcing. And so just to quickly look at the global picture, if you have an increasing trend from your 1970s in pH, you get a more positive. Okay, thanks, Paul. And if you don't there, so it's really highlighting the importance for aerosol forcing for this sulfate aerosol formation dependent on pH could be. And so just quickly, then I've done some initial testing in a branch, which maybe Jane doesn't like, but I've never carried it on any further than this, where we went back and looked at what was previously done in GLOMAP mode, where we valued the pH based on different SO2 concentrations. So this is some initial work where I tested this, and this is summary of now, if I vary it on the sulfur dioxide concentrations, I can get this more spatially varying pH. And that's the difference to the value of 5. So you can see you lower it over the polluted regions and you raise it over the remote regions. And then these are the effects this changing in pH based on SO2 can have on your SO2 concentrations in the top. You can see you lower and raise it, and then you can have on sulfur aerosol at the bottom. So again, a little bit of work's been done on this, but I need to do more to understand what's actually happened when we do this very simple test. So my last slide, then hopefully run through this very quick. So I want to look at a bit more of this initial development branch to look at how these varying pHs now affect SO2 and sulfate concentrations, and what we're actually doing. Is this a right way of calculating it? But ultimately, what a better way would be doing it is to improve this rather than just base it on SO2, as we have more sort of acid-base balance by some of the major acidic and basic species there, and we can get this spatially and temporally varying pH and hopefully improve some of our representation of aerosol formation in the aqueous phase. There, hopefully done in the time, hopefully, Paul.
Yeah, no, thanks, Steve. That was fantastic. Is there a quick question for Steve whilst Anthony gets ready for his talk? Don't see any.
I've got a quick question, Colin. Yeah, but does this add any particular cost to the calculations, Steve?
So this simple way of basing it on SO2, I don't think it really affects much because it's just a very simple function. But I think if you were to put a slightly more complicated one in, then possibly yes. And that's the bit I don't really know because I've never put much more complicated in than just basing it on SO2 concentrations. So yeah, that's the more unknown, and that's why it'd be good to do a bit more testing of how much this would add to it, but hopefully not too much, I'd say.
Okay.
Okay, excellent. Okay, so I'm going to talk about some developments that I've been making on a nitrate scheme in UKCA mode. So this is quite a simple nitrate scheme. And then I will talk about dust briefly. So there have been quite a few people working on this, you can see in that slide. So I'll just run over the model very quickly. So in this model, nitrate and ammonia are emitted into the two smallest soluble modes using a thermodynamic equilibrium parameterization, whilst this nitrate is also condenses onto sea salt and dust using a first order uptake parameterization. I guess the novel thing about this model is that we are limiting the rate at which equilibrium is reached in the ammonium nitrate formation using condensation theory. And I've been looking at the sensitivity of the first order uptake theory to changes to the uptake coefficients. So I have two simulations, fast and slow, depending on the uptake coefficients. The big thing, I guess, to say about this scheme is that it's now on a trunk. You can see the ticket 5262, and that's mode setup 10. Okay, so I'm just going to run over a couple of the results from these simulations. So the fast simulation has a fast uptake rate, slow simulation has a slow uptake rate based on values from the literature. So firstly, looking at the surface concentration, and you see that the areas where you get this ammonium and nitrate are mostly focused on ammonium emitting regions in the US, Europe and Asia, which is reasonable and compares well with the observations, whereas this coarse mode nitrate is much more spread out over the oceans. From comparing the nitrate and ammonium concentrations to observations from CASTNet, we can see that the slow simulation seems to get the magnitude of the concentrations really well. This picture was developed by Catherine, So that's positive. It seems that the model's doing the right thing in terms of ammonium and nitrate concentrations. Looking at the seasonal trends in surface concentrations over the key ammonium nitrate regions, we can see that the trends in surface concentrations are very closely aligned with the ammonia emissions, which suggests that the ammonium nitrate is limited by the amount of ammonia. So Steve Turnock's done a little bit of work for me looking at the particulate matter concentrations and the effect of added nitrate. And the good thing that you see is that the PM 2.5 is not broken by the addition of ammonium nitrate. And in most regions, the addition of ammonium nitrate seems to, if not improve the model, then not do particularly much, apart from over Europe, where there seems to be this anomalous increase in PM 2.5 concentrations when you add ammonium nitrate, and that seems to be related to spurious ammonia emissions in the CMIP6 ancillary files. One thing that you can look at from these simulations is the diurnal cycle of ammonium nitrate concentrations, and you see that it matches well with UK observations from 2 super sites. The concentrations peaking at night and early morning, and then there are lows in the afternoon, and this is largely captured by the model. Looking at the change in optical depth in present day simulations, it ranges between a reduction in optical depth if you add ammonium nitrate and this coarse mode nitrate in slow, and this is because of changes to the optical properties in UKCA rad-air, and an increase in fast of a very small amount, 0.005, although there are quite large regional changes over Asia and Europe, and an effective radiative forcing of between minus 0.07 watts per square meter and minus 0.19 watts per square meter in fast. And so there are significant negative radiative forcings when you add ammonium nitrate over India, Europe, and Central Africa. So this is just to say that there is a paper in development. We're very close to completing the paper, in which we're using the observations of concentrations to basically say which uptake coefficient parameter choice is better between fast and slow simulations. Okay, and that's basically it. I'm actually too quick, but I'm happy to take questions.
Yes, and are there any questions for Anthony?
Yeah, I've got a question. It's Graham Mann again here from Leeds. Hi, Anthony.
Hi, Graham.
Yeah, I was just going to ask. I mean, we had a case PhD studentship with a hybrid dissolution module, the HYDIS module that we published in 2016 in the GMD paper. And this has an equilibrium configuration, or it's a hybrid kinetic or equilibrium solution. Mm-hmm. And we did some testing. I'm just interested in relation to this aerosol cloud interaction. It would be interesting to compare the influence of the nitrate on CCN with what one concern we had with the equilibrium scheme is its influence in growing the smaller particles to CCN sizes changes when you use the equilibrium approach. So it would be interesting to see whether your equilibrium scheme here gives that similar behavior.
So I would say that this is
found in a thesis, and Francois found in his paper.
So I have run instantaneous equilibrium simulations as well to look at the impact that assuming an equilibrium, instantaneous equilibrium means. But I would say that this is kind of quasi-instantaneous by the fact that I am limiting the rate that equilibrium is reached by kinetic theory, by condensation theory. But I would like to compare the results of HYDIS with this model for some simulations. I think that'd be really interesting at some point. I haven't really looked at the aerosol cloud interactions yet. I had a brief look at the CDNC, And there were some significant regional changes in the ammonium nitrate regions, but it would be good to look at the aerosol cloud interactions at some point as well.
Okay,
It's great work.
Anthony, do you have your dust talk ready?
And
Yeah.
it'd be good to make sure we understand the influence on the indirect effect as well.
Yes, definitely.
Thanks.
Thank you. Okay, so I've also been working on dust. This is work also done with Steph Woodward and Jane in ESMS. So looking at the addition of a third insoluble mode and sensitivity to aging rates. So previous studies have, which I've performed and which Steph have performed, have looked at the UKCA two-mode dust scheme, and they found that there is too much dust away from source regions when aging isn't turned on. But when dust aging is turned on, i.e. when insoluble dust is permitted to become soluble, a significant fraction of the dust becomes in the soluble mode. So what we've done at the Met Office is we've come up with this work plan to improve the UKCA mode dust scheme to make it operational and to replace classic. And the first task is to add a third insoluble mode, a giant dust mode to the model, and then to look at process level things like improvements to sedimentation, impaction, scavenging, etc. So what I'm going to talk about briefly is the addition of a third insoluble mode and the impacts that makes on UKCA dust, and also looking at sensitivity to aging. So in a branch, this is not on the trunk yet, I've created a mode setup 12, which has a super coarse insoluble mode with a width of 1.8. And I've reduced the width of the current coarse insoluble mode to 1.59. I made sure that the super coarse mode is relatively interactive, and I'm testing some different emissions mapping. And then in a separate experiment, I'm looking at the current UKCA aging in the two-mode dust scheme. And I've looked at the sensitivity to changes to the number of microlayers, which are used as the threshold for aging. So by increasing the number of microlayers, I expect to reduce the rate at which aging occurs. So I've run quite a few simulations, and this is all very preliminary analysis. I have a report which goes into this in much more detail if anyone wants to see that. And this is basically informing the development of the UKCA dust scheme. So firstly, looking at the dust optical depth and comparing it with classic and also with CAMS reanalyses. So the map at the bottom is the CAMS reanalyses product, which you can assume to be the benchmark. And you see that classic does a really good job of getting the dust optical depth, primarily in the dust emitting regions. There seems to be possibly too much dust reaching the high latitudes. And I guess the big thing from this paper, from this figure, is that the free modes addition of third insoluble mode does not seem to be appreciably different to the two modes without aging. However, when you turn on aging within the two-mode scheme, the dust optical depth becomes much more similar to classic and to CAMS, and so it seems that UKCA dust really needs some form of dust aging in order to produce realistic optical depth. So one thing you see from this time series figure and from the associated pie charts in the bottom right corner is that there is this huge amount of dust which is in the soluble modes. Okay, so now looking at the soluble burden in these two-mode simulations with aging, you can see that 50% of the dust in the first simulation and 30% of dust in the simulation in which I've slowed aging is in the soluble mode. And one thing is that from the previous studies, this has been seen as an issue because the idea that dust is soluble has been seen to be wrong. So this is a question that we really need to talk about. So now looking at the near surface concentrations in these simulations, and basically the middle two plots show the dust concentrations in the free mode simulations, and you see that they're just too high in these remote regions over the North and South Pacific, and this is similar to the two mode simulations without aging. But when you turn aging on, the dust concentrations over the South Pacific and over the Atlantic Ocean are much more comparable to classic and to CAMS. And so it just, all of these results seem to point to the fact that some form of aging is needed. Thank you, Paul. Some form of aging is needed in the UKCA dust simulations to get the concentrations in AOD the same. One thing that you can look at from these simulations is the amount of dust that's removed from wet deposition. You see that over classic, most of the dust over land is removed from dry deposition, and then as soon as it gets to the ocean, it's removed from impaction with precipitation. And ultimately in the UKCA simulations, there's much more dry deposition. You can constrain this with observations, and it seems that the classic is producing too much wet deposition and the UKCA mode is producing too much dry deposition. And so one thing that we might want to look at is changing the impaction scavenging scheme in the two mode simulation. So really this project has asked more questions than it's answered. So is it really necessary to have a third insoluble mode when the two mode scheme is doing so well with aging on? Is having a significant fraction of dust in the soluble mode wrong? The aging rates seem to be too high. The mass accommodation coefficient has been set to 1 for some reason in the insoluble mode. And so I'm going to perform more simulations where I reduce this to more realistic values. And do we need to look at the changes to the sedimentation and the impaction scavenging scheme to improve the representation of wet deposition in UKCA mode dust? Okay, thank you.
Great, thanks again, Anthony.
Thank you.
Be helpful if people could raise their hands virtually to ask questions, but do I have any questions?
I don't know how to raise my hand, so I can't see it on mine.
Okay, great. Hello, everyone. It's nice to be presenting here, and thanks for the opportunity. So I'm going to give an overview of a couple of topics on which we have worked recently. And these are to do with ozone dry deposition to the ocean and lightning produced NOx, looking particularly with UKCA, but the results we have got are sort of more generally applicable. And the aim was to improve these processes in a global model. So the contributors to part of this work or all of this work are my colleagues, Ian Galwally, Matt Woodhouse, Marcus Teixeira, and Luke Abraham from Cambridge University. And I have a number of acknowledgements there, and really grateful for those. So the first one is to do with dry deposition of ozone to the ocean. Dry deposition of ozone at the surface is a significant sink of ozone, and thus it affects mixing ratios of ozone in the troposphere quite a bit. The current estimate of global ozone dry deposition is around 1,000 teragrams per year, of which about 30 to 35% is to the water surface. Hardaker et al. Recently showed that the dry deposition of ozone to water has the largest uncertainty out of all the other surface types. So it's quite an important area that we thought we should look at. And the deposition is calculated through standard method where you have three resistances, the aerodynamic resistance, viscous sublayer resistance, and the surface resistance, RA, RB, and RC respectively. For the water surface RC, the surface resistance is the dominant term, and most models assume that it is constant at about 2000 seconds per meter, and that is what is used in the UKCA as well. And the model we have used here is Access UKCA, which is basically UKCA at version 8.4. So we calculated deposition velocities over the water surface using this setup and compared the results with cruise-based measurements of Helmig et al. And what we find is that the model overestimates these deposition velocities by a factor of 4. So these are the model values here, and these are the observations. So these are basically the value you get is inverse of that, which is because this is the dominant term in this deposition velocity expression. So what we have done here is we have developed a mechanistic process-based scheme for calculating the surface resistance RC in the deposition velocity calculation for water surfaces, and it basically solves mass and flux conservation equations in two layers. In water here, layer 1 and layer 2, and it is based on the approach of Ferrol et al. And it includes all these water-side processes, solubility of ozone, molecular diffusion, turbulent mixing, and the chemical reaction of ozone with dissolved iodide. And this is actually the equation we get for RC, and this includes all these processes based on or following on from these two equations. So we have put this equation into UKCA, and the results we get using this new scheme are these here. So this is what we were getting originally, and this is what we are getting now. So you see that there's quite a bit of improvement in the deposition velocity calculation over the ocean. And if you now look at the ozone distribution over the globe and the distribution of the deposition velocity over the globe here, you would see that, so this is the difference, or this is the percent overestimation of deposition velocity by the default scheme. So you see that with the new scheme, and you compare the new scheme with the old scheme, you see that the old scheme actually overestimates the deposition velocities by as much as 300% or even 350% in some areas. And this overestimation increases as you move from mid latitudes to high latitudes. This is the percent change in the near surface ozone, and you would see that with the new scheme, the near surface ozone increases by up to 16% in high latitudes in the southern hemisphere. So this is sorry, this should be positive. This is new minus old, not old minus new. And we have done quite a bit of comparison with observations of ozone over the ocean or close to the oceanic surfaces or coastal areas. And here there is one example here, which is Cape Bream, Tasmania. So this is what we were getting using the old scheme, and with the new scheme, you see that there's quite a bit of improvement in ozone near the surface at this particular site. And as I said, generally we get quite a good improvement all over the globe. So what happens when we include this new deposition scheme for oceanic surfaces in UKCA? We see that the ozone deposition is reduced from about 300 teragrams per year to 100 teragrams per year, which is a reduction of 65% over the current estimates. It reduces the global deposition by about 20%. So we get 800 teragrams from 1,000 teragrams, which we had previously. And here there is some comparison with other studies here. So we see that with the UKCA, the land-based deposition, dry deposition of ozone is pretty similar to these other studies, but we see that with the new scheme, the deposition to the oceanic surfaces is now only 1/3 of what these other studies are suggesting. And these all basically use the Wesley scheme, where we have constant surface resistance.
Ashok, you've had 8 minutes.
8 minutes have gone. All right. Okay. So, so there's a huge difference or significant difference caused by this new scheme, and it leads to an increase in the tropospheric burden as well. And this increase in the tropospheric burden is in the right direction. This scheme has been included in the trunk at version 11.4, and there have been other studies which have used this particular scheme in other models, which I have given here. So the next one is lightning produced NOx in UKCA. So lightning is a significant source of NOx in global models, but there's a lot of uncertainty in its estimation. And as you can see from this range, that it is quite uncertain. And the way we calculate lightning NOx in these models is that we first calculate a lightning flash rate based on the convection scheme in the model, and we multiply that by NO emitted per flash. And most models use this particular scheme, Price and Rhine scheme. These are the equations here, and this is what UKCA uses as well. And so these are the satellite observations here of flash rate, and this is what we get from UKCA. So you can see that over land, things look pretty good, but over the ocean, the model underestimates the flash rate by quite a lot. So these are the average values. So we looked at this as well, and went back to the literature and found that there are some theories developed by various people. And in this particular case, we took this particular reference and used their approach and calculated these coefficients based on observations as well as some theoretical arguments. And we have come up with these new parameterizations. And this is for land, which is very similar to Price and Rhine's parameterization, but for the ocean, it's very different. So this is Price and Rhine, and this is what we have now. So this is UKCA result with the new parameterization. This is the old one, and this is the climatology. So you see that there's quite a bit of improvement in the oceanic distribution of the flash rate. And when we put this into UKCA, these are the differences we get. So there's a 38% increase in the global lightning NOx from 4.8 to 6.6 teragrams of nitrogen per year. And these are the differences between these two schemes, new minus default. So the global increase is about 15.7% in NOx. And this leads to a global increase of 8% in ozone. And here there are some comparisons with ozone sonde data. So PR92 scheme, new scheme. Overall, the new scheme does better than the old scheme, particularly over the southern hemisphere. Other species are impacted as well: hydroxyl radical, methane lifetime, carbon monoxide, and as I said, larger impact over the southern hemisphere. There's a paper on this, and this scheme has also been committed to the trunk. So that's all I have to say. Thanks for that.
Thanks, Ashok.
Thank you, Paul. Yeah, so I'm just going to give a very brief overview for some of the work that we've been doing, looking at kind of stratospheric ozone biases, well, total column ozone biases really in the UKESM1 model. And I'd like to thank the team of excellent people that have been kind of like really contributing to this over the last 12 months or so. So many of us on the call had a paper which has now been published evaluating total column ozone, predominantly in the historical simulations from CMIP6. And we created figures that look like this. So on the left is 60 south to 60 north average total column ozone, 1850 to 2014. And then on the right, the same data, but kind of normalized to the 1980s values. And what we see alongside the kind of story, the classic story of CFC-induced ozone depletion, is that the UKESM1 model, this purpley color model, has a very significant total column ozone bias compared to the CMIP6 multi-model mean. So on the order of about 40 Dobson units in the pre-industrial as an absolute value. And then when we normalize the time series on the right, what that equates to is effectively much stronger ozone depletion with the onset of CFC emissions, which of course will have a fairly sizable regional climate signal associated with it. So if you can see the cursor, UKESM1 is this kind of flat purple line, and then the kind of lowest one on the right-hand edge of this figure. And that's chiefly because there's just more ozone to deplete. So when you normalize it to a high value, you end up lower when you have CFCs. So if we focus on UKESM1 in particular and try and identify where that column ozone bias is coming from, I've plotted here the zonal mean ozone mixing ratio on the left, CMIP6 multi-model mean on the right, and then the difference. And we see that chiefly the bias kind of breaks down into three regions. There is high ozone in the kind of middle upper stratosphere at most latitudes. There is very high ozone in a percentage term in the kind of tropical lower stratosphere and around the tropopause. And then there is high ozone in the tropical troposphere. And of course, there's not much. The ozone mixing ratios in these regions are low, but for the column, this is quite a sizable contribution because the mass of the atmosphere is obviously very large here. So when we kind of integrate in our minds these percentage zonal mixing ratio change, we have to take into effect where the column is kind of dominant as well. So as I say, chiefly, you know, basically ozone is high everywhere in the stratosphere except for perhaps the polar lower stratosphere and around the kind of tropopause. So these are these regions here. And to cut a long story short, a lot of work went into this trying to chase down potential bugs in emissions and dynamical problems and stuff. But chiefly, we could resolve a lot of this bias by 4 fairly simple updates, really, rather than large code changes. The first was to update the files that FastJx uses. FastJx is the photolysis scheme in the model. Particularly here, changes to the photolysis of nitrogen species is key. We've also changed how we treat tracer kind of conservation at the top of the model. So previously there's been this sponge layer in the top 3 levels. We've changed how we treat that, and that has a significant improvement, particularly on water vapor. And then water vapor is a source for Hox radicals, so that helps us get rid of some ozone. We've added additional heterogeneous chemistry, which is described in Fraser Denison's paper from a few years ago. And we've also updated just all the biomolecular and termomolecular reaction rates. And when you do these, and as I say, these aren't major code changes, these are fairly innocuous kind of updates to rates that had just got kind of old. you see quite sizable changes in ozone. So here is the impact on the zonal mean ozone mixing ratio, and on the right, the column as a function of latitude versus time. And the net impact of all these changes is to reduce ozone everywhere, but particularly in this kind of upper mid-stratosphere layer where we saw quite high biases, so that's positive. But a deepening of, thank you, Paul, a deepening of the Antarctic ozone hole. And that's something to bear in mind. But so the impact of these changes is to reduce ozone, which is good because we were high. And so then if I plot this as a time series, this is column ozone again, 1850 to 2014, the subset of the models from the previous figure. These updates give us the blue line, which for the kind of 1980 to 2014 period, which is the period for which obviously we have observations, we agree very well with the CMIP6 multi-model mean. And then as you go back in time, we're still a bit higher than the CMIP6 multi-model mean. Part of that is a spin-up kind of induced effect. On day one, we started from the pink line, and so some of this is spinning up. But also partly, we have to think of ways that we can move away from evaluation against the CMIP6 multi-model mean, because otherwise we are assuming that is correct, which is, there's no observations really pre-1970, good satellite observations where you got ground-based ones, obviously. But okay, and so then I'll just finish briefly on a kind of philosophical point, which is, how did we get here, and do we need to think of, rethink the way we do model evaluation? And so one question you might have is, how is it possible that column ozone ended up so high in the CMIP6 simulations that we ran? And the answer there, I think, really is that these models are now so complex, particularly the chemistry, that if you are asked to evaluate one part of it, you end up producing usually one figure. There is this thing, the UKCA evaluation suite, which produces a single snapshot against the climatology. Certainly evaluation against time series would be better. And that's exactly what Alistair Seller did in his paper. But actually he showed very nicely in his paper that if you looked at Antarctic ozone depletion, the model does an excellent job, particularly for the spring period, so this kind of classic ozone depletion period. But actually, if we were to look at almost any other month or any other latitude, this bias would be quite clear. So I think this really highlights a weakness in the way we evaluate models, which is to, go in with a preconceived idea, which is that, if you are modeling the Antarctic ozone hole correctly, you're probably doing a good job. And actually, I think we need a more rigorous statistics-based approach to identifying these biases much earlier in the day. And I'll stop there. Thank you.
Yep, that's great.
Okay, so thank you very much. I'm going to talk about dry deposition, and I've added in here what I will call flexible surface tiling. So first, great to be here, but I'll also acknowledge that I've been working with colleagues at CH and also within some of the UKCA team. Ashok has actually introduced this, so I'll just skip over these, but this is what I'm looking at is the dry deposition scheme within the UKCA. So Ashok kind of very quickly introduced it, so I'm grateful there, but so I'll just skip over this in the interest of time. So this scheme that's used in the UKCA is based on a Wesley scheme with some updates. And it links to the JULES land surface scheme in the sense that some of the parameters that are used for the resistance terms are based on JULES related outputs. I just want to bring in here that some years ago, Federico Centoni, who was a PhD, did a PhD through UKCH and the University of Edinburgh, and he introduced a full implementation of the Zhang et al. Scheme, which allows for stomatal blocking when when vegetation is wet. So these are the future requirements. These, I guess, are more the current requirements. So what I would just to skip on is that 4 years ago, we had a kind of consultation and a workshop And some of the messages that came out there was to get more consistency between UKCA and JULES as more land surface types are added. We're also interested in deposition to the other surfaces, so the ocean and the cryosphere, and Ashok again has talked around about the deposition of ozone to the ocean. On the aerosol side is, from what I see, is that, it's based very much on the land surface type, with some parameterizations and lookup tables that we've moved to a more process-based approach. And then strategically and looking very long term is that, that the intention would be that we would do the full surface exchange for trace gases. So i.e. deposition, emission, and also the kind of re-emission and planetary boundary layer mixing. So this would be very similar to the approach that's used in the for the exchange of energy water between the surface and the atmosphere, and also the carbon. So very early on and following, because of that, because JULES has kind of two roles when it's coupled into the it's both the land surface model, but it does the surface energy exchange for energy and water and carbon with the other land surface components, that it made sense to put it into JULES rather than creating new interfaces. So the idea was that UKCA would provide a surface concentration, and that the deposition scheme in JULES would return a flux. So the benefits of that would be that the UKCA would not need to know the details of the surface, and this would allow flexible tiling, and it, removes some of the current limitations that only 4 specific surface type configurations are allowed in the UKSM. So I don't have results in terms of lovely maps and things to show you, but this will be more a kind of update. So there is in the JULES trunk at release 5.5 the kind of deposition infrastructure for the input-output. I have working branches at JULES 5.9 and UM 11.8. So I've pulled in the UKCA gas phase routines. So there's a version that is UK as is. So it's largely the UKCA coding, with obviously just a few cosmetic changes to get it to work within JULES. And I have an equivalent where I have what we call flexible tiling. So essentially a lot of the resistance parameters are passed through nameless rather than hardwired into the code. And this also removes the restriction on the permissible surface configurations. I've been looking at this in JULES, trying to work on the original philosophy of taking a UKCA surface concentration and returning a flux. So that's kind of work in progress at the moment, and I've been talking to Luke and John Hemmings particularly. So I have a number of suites. In terms of testing, when I was developing this, I was had a very offline version, so I could drive the deposition routines with essentially create some data set of the driving parameters that are passed to the routines and just run those offline. As part of this work, I've identified some coding issues, which one of those has been corrected by Alan Hewitt. And recently, in trying to compare the parameters that were being passed to the UKCA deposition routines with those that I was finding in JULES, I've identified that there are a couple of further coding bugs that I've just reported into the UKCA. So in terms of next steps,
1 minute, please, Gary.
Yeah, I'm kind of home.
Thanks.
So I've been comparing the inputs to those and the outputs, and the idea then would I need to extend it to all the deposited UKCA traces. So one of the things that I've had to do, but I think will probably be needed, is to develop some form of pre-processing code to create the deposition name list for the particular configuration and the traces that are being used in the run. So I had a conversation with Luke and John Hemmings earlier in March. We're talking around how and where to pass fluxes back to UKCA. There's obviously issues around creating deposition diagnostics, and clearly in looking in terms of, I think there's a very strong interest in trying to get this into or relevant code into the trunk to allow the flexible tiling. So where I'm at the moment in terms of there is in one sense to take a step back, is to basically just call the JULES-based UK equivalent from the same place in the UKCA as it's called at present. So that's a task that I've kind of got in hand. And I probably just added a late addition here, but probably just to flag it, and it may well be that it's covered, is that there is ozone vegetation damage. So this is not quite deposition, but I think it was something I've added in, is that there is ozone vegetation damage available in JULES. And I know in terms of discussions, particularly around the NERC Centre's global change future work, that there will be interest in methane mitigation scenarios. And clearly one of the benefits of methane mitigation through reductions in tropospheric ozone concentrations is obviously to reduce ozone vegetation damage and thereby increase carbon uptake. So clearly that exists in the JULES standalone. So my question, and I think it's hopefully Gerd or someone might be able to answer, is whether that's fully coupled in the for the UKSM. So thank you.
Thank you, Garry.
Okay, thanks, Alex, and hello, everybody, and good morning to those in the morning. I'm Zhenze. I'm from the University of Edinburgh. Today, I'm going to show you some development work in the UKCA. So we care about the surface ozone pollution and high emissions of China. But when we first use UKCA to predict ozone levels, we find the model always underestimate the ozone levels. So does the model tell us that there's no ozone pollution in these areas? So it's not the truth, but I'm sure that high NO titration in these areas must be one reason that leading to much lower ozone levels. But another potential reason is that ozone production is not sufficient. So based on other studies, we found that reactive VOCs like alkenes and aromatics are quite important to ozone production in industrial regions of China. But the disadvantage of UKCA is that UKCA nets these traces. So based on the standard UKCA chemistry scheme, we just incorporate these higher and reactive VOC traces. So specifically we add propane and butane and taurine, and they are added as proxies as reactive VOC and classes such as alkenes, butanes, and aromatics. So we highlight these provide a more active photochemistry or VOC oxidation environment, which is suitable for China situations. So we are not only looking at the monthly mean data of ozone levels. We also want to look at the diurnal variation of ozone or other air pollutants. So it's important that emissions can also have this diurnal or vertical profiles. So, but diurnal and the vertical profiles of emissions can be different based on different emission sector. So we divided the emissions into 5 sectors, only for anthropogenic emissions, and they are divided into industrial power plants, residential transport, and one actual agricultural emissions only for ammonia emissions. So that means an individual diurnal and the vertical profile can be imposed on each emission sector. So if you're interested in the implementation of the codes, you can check out the code branch here. I listed here. Here's some basic results. I show you about the comparison between the standard and the updated chemistry scheme. There are 2 columns in this page. The left column shows you the situation in the winter time, and the right column shows you the summertime situations. And you can see that there's a pretty similar ozone spatial distribution patterns between those chemistry schemes, but there's some regional differences, especially in South and East Asia, with much higher surface ozone levels, and that's what we expected. Also compare the troposphere ozone burden and the ozone burden in the planetary boundary layers between 2 chemistry schemes, and we find that they're about 5% higher ozone burden in the updated chemistry scheme.
Just to say, you've had 4 minutes.
Okay, yeah, but the lifetime in both chemistry schemes are quite similar. So in the case that the more active chemical system seems that is still able to remove ozone as efficient as the less active chemical system. So we also evaluate the surface ozone data against polar ozone data. So similar to other previous studies, that there is a systematic bias low in winter time, but this bias high in summertime. So I suppose there's some processes related to seasons might not be right. For example, in winter time, the mixing the planetary boundary layer might be poorly constrained, but in summertime, the biogenic emissions might be overestimated. So there's some physical or chemical processes that are related to these ozone biases. So that's all. Thank you very much.
Thank you, and thank you for.
This proposed improvement for UKESM2 is really about putting in coupling between the interactive photolysis scheme FastJx and GLOMAP mode. Currently, FastJx knows nothing about aerosols except through aerosol impact on cloud. So we'll hear a bit more later on about chemistry and aerosol coupling. So clearly gas phase chemistry has a strong influence on aerosols through changes in oxidants or through the production of VOCs that have very extremely low volatilities. But I'm talking about the coupling in the other direction, which tends to be weaker. So we know, for example, heterogeneous chemistry has a strong influence on chemistry, particularly in the stratosphere, but also in the troposphere. And of course, aerosols can influence the chemistry through photolysis. So they may do that through the impact aerosols have on cloud, and we've seen evidence of that in the AirChem MIP simulations. But of course, aerosols can also influence photolysis rates directly through the scattering or absorption of radiation through aerosol radiation interactions. And it's this particular coupling that I'm going to address here. So why do we care about this coupling, and what is its impact? These are plots from a paper by Michael Holloway that was published in 2019, where he's looking at polluted regions. So he's looking at Beijing in summer and winter. And the plots here are showing the impact of aerosols only, cloud only, and the combination of aerosol and clouds on photolysis rates of JO1D and JNO2 relative to clear sky photolysis rates. And you can see here in the winter time that the aerosol only effects on photolysis rates in red are having a bigger impact on photolysis rates in the boundary layer than the clouds. And you can see that's also true in the summer in much of the troposphere. Now these are polluted conditions, so on a global scale these impacts would be smaller. This again is taken from that same paper by Michael Holloway. So again, looking at polluted conditions, and this is now looking at the impact of aerosols only on photolysis rates. In this particular case, it's JNO2. And you can see the impact through the diurnal cycle, both in winter and summer. So we can see a reduction in photochemistry in the boundary layer, both in winter and in summer, with enhancements in photochemistry aloft. And in addition to this impact on photochemistry, but also that can feed back on the aerosols themselves. So in terms of this particular work, the aim here is to introduce the direct coupling between aerosols and photolysis rates. There is a code branch already available at version 10.8 with some documentation under that ticket, and they're courtesy of work that Michael Holloway did at the University of Lancaster. In terms of next steps, then they need to be, that branch needs to be upgraded. I think there's more testing, assessment and documentation to be done, but my aim is to lodge that at the October-November code freeze. And then, as Jane pointed out earlier, then there would be some additional testing required in terms of in terms of possible UKESM2 inclusion, namely a ticket, corresponding testing and assessment and documentation. But the good news is that we do have some funding and have a commitment to do this under a new EU Horizon 2020 project, which is starting in June. So that was all I was going to say.
Fantastic. Thank you, Fiona. Thank you for keeping well to time as well. We can take questions again on.
Okay, so there's the carbon cycle is shown by the red arrows, and then the soil nitrogen cycle is in the grey arrows. So the interaction with UKCA would be through the deposition and gaseous loss of nitrogen compounds from between the soil and the atmosphere, and its limiting effects on the carbon cycle is through reduction in the productivity of vegetation, and also potentially through reducing how rapidly litter is decomposed and respired back and carbon is respired back to the atmosphere. But in practice, we don't see that effect very strongly in the model. So from the land point of view for UKSM, we've got sort of a list of our priority developments, and the ones which might most strongly interact with these nitrogen emissions would be vegetation fire interactions, which would in particular could link to nitrogen emissions from fire, from burning, and then also potentially, hopefully we can manage to get layered soil carbon and nitrogen, so we'd have a profile through the soil column of these pools and fluxes. And then it's not a sort of code change, but there's a lot of more we can do to understand the nitrogen scheme as it currently is, and potentially more tuning we can do. So that again could vary how strong these fluxes will be. So the potential couplings are we can easily take in nitrogen deposition from UKCA, and we can potentially supply nitrogen emissions. At the moment, we've just got a nitrogen gas loss term, which is just a sort of a diagnostic. So it's a case of partitioning that into species for UKCA to use. But there's a more complicated nitrogen scheme in JULES called a COS, which is not ready for UKSM yet, but it does split these compounds into species for the atmosphere, so we could pick up stuff from that. Another coupling we could do is to better link the fire emission scheme to the vegetation carbon and nitrogen scheme, because at the minute it doesn't sort of conserve nitrogen or carbon. So potential issues are, I mean, I'm not sure how sensitive the land is to deposition, so it might be, I guess it's worth investigating that first, because it might be a lot of effort and then it turns out not to be very sensitive. And then also the emissions from the land surface might not be that realistic, so we don't want to sort of end up giving UKCA something rubbish. So it's something to investigate really probably before we get stuck in with coupling. At the minute, with now we've coupled the vegetation and the soil nitrogen, the scheme is very slow to spin up, and if we include coupling with the atmosphere, that might become more of a problem. So that's something we need to bear in mind. And as I say, the fire emissions does not currently conserve carbon and nitrogen. So just quickly, some results showing how strong the nitrogen limitation is. And it seems, so in the bar chart on the left, there's it shows the potential increase in productivity if there was no nitrogen limitation. So that's kind of an indication of
You've had 4 minutes, Eddie.
Okay, if you're above the 1 line and you gave the plants more nitrogen, they would be more productive and take up more CO2 from the atmosphere. And that's the case for all biomes basically, but more strongly for some biomes, such as the tropical savanna here, has a very large peak showing it's nitrogen limited. However, if we look at how this looks like, what this looks like on a map, you can see lots of regions are dark green, showing there's basically no nitrogen limitation. So it's quite regional as to where this happens, which is much like nitrogen deposition will be a regional process. And then in some cases, it's quite high in regions with low productivity. So while the ratio of your productivity increases is large, in absolute terms, increasing productivity in the outback of Australia isn't going to do much. Okay, that was my summary.
Fantastic. So I'll be showing results on coupling interactive fire with atmospheric composition and climate in UKESM. So fires are an important component of the Earth system. They can change the land surface by burning vegetation, but they also act as a source of emissions to the atmosphere, changing atmospheric composition and having an impact to their feedbacks. And the impacts that fire have on Earth's climate remain a bit uncertain, making this quite a relevant topic of research. In JULES, there's the land surface of the there's a fire model called Inferno, but this is not available or was not available to the so there was no interaction with the atmosphere whatsoever, so it wouldn't see the model atmosphere, and there was also no interaction with composition with UKCA. So what I've been working on is coupling this fire model, Inferno, to the atmosphere and composition. So Inferno is a very simple fire model, but it gives quite good results in the Earth system kind of scales. It takes precipitation and temperature and relative humidity from the atmosphere to calculate the flammability of the vegetation, and it joins up information from the land surface like fuel density and soil moisture to calculate this. It also has a source of ignitions to calculate when does a fire start, and these comes from lightning, which is diagnosed by the atmosphere model, and also the an ancillary data from population density. So the more population, more fires we have until we reach a point where there's big cities and with a lot of population where fire suppression is also important. One aspect that was also added to this model was the inclusion of socioeconomic impacts on fire ignitions through the addition of parameterization using the Human Development Index. So richer areas of the world will manage fire in a different way, so they will have more money to put into managing fire in a sustainable way, so they will try to mitigate fires as well. With this information, Inferno calculates a burnt area and for a given grid box, and from that burnt area, using emission factors, we get to the emissions that are then passed to the atmospheric composition model, in this case UKCA, and this will interact with the atmosphere throughout the aerosols effects and and greenhouse gases effects, which then will change the fire conditions, feeding back to Inferno again. So this gives a nice way to get the feedbacks from fires. Lately, I've been working on an evaluation of how this fire model looks like in UKCM context. I've used AMIP simulations to look at this. And in here, I'm presenting a comparison between GFED, which is the very well-known observation from fire burnt area, and the results from UKESM with fire enable. I must stress that in this configuration of the model, there's no vegetation fire feedback, so we are always burning the same vegetation over and over again. And this looks quite reasonable for a fire model, so we are burning in the main fire regions, which is good. When we have a bit of an underestimation, especially over Africa. This is reflected in the emissions. So emissions depend on the burnt area, but we have, in this case, an overestimation due to biases in the underlying vegetation. But it's emitting in the right places, so these early results look quite promising. Yep. So we know what the limitations are and that are creating those biases. There's forests in Africa where savannas should exist, which emit more, and there's other future work needed to include the fire vegetation's feedbacks, which will be quite important, and to include peatland fires as well. Yeah, that's it.
Good morning, everybody, and good evening, as the case may be. Can everybody see the slides now? Good, great. So I'll try to keep that short. This might be my famous last words, but I'll at least give it a try. So I have two things I want to draw attention to today. One is the progress on getting the emission-driven version of UKCA into the trunk. This is going on currently. So just to give you a bit of a background, we've been developing an emission-driven version of UKCA for UKESM over the last couple of years. And I'm very grateful for everybody who contributed to that. There were quite a few people involved in that. And this is just to give you an idea of what's been going on. These are a list of changes that we've made, and we have a number of simulations done with this prototype version. Data is available, and I'm currently working on getting the necessary changes to UKCA into the trunk, and the plan is, or the firm goal is, to have that done by the next code freeze in June, or end of May, early June, whatever. So it should be in the next version of the UM. So this is all good and on the way. And as a second point, I want to draw attention to a little bit of a problem that we've been dragging along for a while, and that's the coupling between the aerosols and the BVOC scheme. Kat Scott has drawn attention to that again succinctly and precisely during the Crescendo General Assembly last week. And that is in this multi-model endeavor, there were two models basically that had an interactive BVOC scheme coupled to the aerosol scheme. And there she found a very distinct difference between two of the models, namely UKESM and NOR-ESM. And there is a bias between those two models in that UKESM has a much smaller amount of SOA produced from BVOCs in the tropics. And the reason for that is, in my opinion at least, that we are not taking account of isoprene in the aerosol scheme, but using terpenes as a surrogate. And there are two problems with that in my mind. One is that terpene emissions are not CO2 inhibited, and they are predominantly emitted in the extratropics, whereas isoprene is CO2 inhibited and predominantly emitted in the tropics, which will cause a substantial bias in the model, I think. I haven't done any work on that, but I've learned that James Webber at the Cambridge University is working on this, and he will come back to that topic later on during his talk, I understand. So thank you for Kat. Thank you to Kat and for flagging that up, and thank you for James and for doing the work on that. So I think it would be wise to at least have a think about that before we go into using the same setup in UKESM 2.0, but we'll see what can be done. So basically, that's all I wanted to say. Development on the emission-driven version is going on and progressing well, and we have a potentially serious bias in the BVOC-aerosol coupling that we need to address. So that's all I wanted to say. Thank you, Paul.
Okay, so I'll talk about solar variability in UKCA, and I should acknowledge Fraser Dennison and Johnny Williams, who have contributed in various ways to this talk. Fraser is now in the TSRO, and I think he's on this call. Okay, so the idea is that we want to implement solar variability in the photolysis schemes, in the two photolysis schemes in UKCA. It's fairly simple. We take the electromagnetic solar forcing data that was provided for CMIP5 or for CMIP6, and this is then decomposed using EOF analysis into an invariant part I0, which is the invariant part of the irradiation, a function of wavelengths lambda, and a part that goes with the solar variability. And so then you have this product I1 times T, so you can see it in this formula. And so this decomposition is shown here. At the top is a sort of non-dimensionalized solar index, the variations are of the order of 1. And you can see in the middle of the 20th century, the sun was a bit more active with larger variations. And then the forecast for the rest of the century is relatively small oscillations. For example, there are interesting variations in the solar activity. The mean solar spectrum is here on a logarithmic scale, basically in the visible range, 400 to 800 nanometers, not a lot of variations, but then as you go into the UV part, it decays, and then in the far UV between 100 and 150, there are some interesting variations in intensity, especially Lyman alpha, which drives a lot of in the mesosphere. And below that is the ratio of I1 to I0, so that's the relative importance, if you like, of solar variations. And that increases as we go to shorter wavelengths. To the point that actually most of the impact of solar variation we can probably expect in the range of wavelengths between 117 and 177 nanometers, which is covered by the offline photolysis scheme. For wavelengths greater than 177 nanometers, we use the FastJx scheme. But anyway, we want to implement solar variability in both of these schemes. Now, the first question is, how good is that decomposition? We only take the leading term, so the constant term and the first term in the decomposition. And so at the top here is the original forcing minus the average term, essentially. And at the bottom here is the first term in this sort of singular value decomposition. And with a naked eye, you can't really see any difference. In other words, the first term captures practically all the variation that's in this forcing data set. That's maybe by construction. Can imagine that the data set was constructed with this decomposition in mind, essentially, or assuming that this applies. And it basically just says that the sun behaves like a proper, hot body and emits, has variations in temperature that are reflected in this variation in electromagnetic wavelengths that come off this hot body. So how do we implement this in UKCA? As I said, we have these two schemes. One is the offline scheme after Larry and John Pyle. Has roughly 1 nanometer resolution in this short wavelengths region. And then there's FastJx, which we talked about earlier. So in both cases, we have to regrid I1, the solar variability term, to the respective 2 different grids for these 2 different schemes. And then at every time step, we simply add this term I1 times T to the invariant part of the forcing, essentially. So it's pretty straightforward. And we note that much of the impact on ozone in particular comes from the offline scheme. And so, so this is demonstrated on the right here, a plot taken from Fraser Dennison's paper, which appeared 2 years ago.
One more minute.
Showing at the top. What? 1 minute? Okay, showing at the top the impact on the oxygen photolysis rate. You can see here in the mesosphere variations of the order of 10% or so appearing. And at the bottom is the impact on the total column ozone. Roughly less than 1% variation is going with the solar cycle here. And so now, why do we do this? So the solar variation projects onto the southern annular mode. Here's the correlation of the solar index essentially with the zonal mean, annual mean surface pressure. And you can see here that there's a typical imprint of the southern annular mode, positive correlation in mid latitudes and negative correlations at high latitudes, meaning that when the sun is in an active state, we have a more likely a positive phase of the southern annular mode. And in the northern hemisphere, this doesn't exist. So anyway, so the scheme is mature. The code is already lodged. I believe it's not updated to CMIP6, but that's relatively straightforward. We used it as demonstrated by this plot in our NZESM simulations of this latest generation of the model. So I believe it's ready to go into UKSM2. Thank you.
Thank you, Olaf.
Okay. So yeah, I'm here to talk about the CRI-Strat mechanism, something that I've been working on a little while. You may have seen me talk about this in a few, maybe the ECHEM meetings and a few other things. Okay, so obviously like 5 minutes isn't very long to talk about a development of this kind of scale, which is essentially a wholesale replacement of the chemical mechanism in UKCA. So I'm just going to sort of touch on the sort of design philosophies of this, what makes it different to the mechanism that's already in there, why we think that would be important. So to take something like StratTrop, this is a little bit of a straw man, but we could say that this mechanism development has kind of happened on the hoof, like you have a sort of basic chemistry that scientists think is going to be most important for the processes that we think are important. We take fundamental parameters, develop that mechanism, add it to the model, and then we have that whole system mix in with all the other processes that are going on the 3D model, try and evaluate that against observations. And, you know, it's often quite a difficult task because you don't really know what are the errors which are due to the mechanism itself, what are due to the other components in the model. And then you kind of have these sort of processes of ad hoc updates as people add extra bells and whistles depending on what their interests are. And, you know, it's still, you know, I still think the StratTrop mechanism is a good scheme and it covers a lot of the bases. That one of the things is that it's very difficult to have an idea of what is actually causing the model errors that we see. And you have these sort of risks of compounding or compensating errors as the mechanism expanded, which due to sort of different levels of complexity. You don't have that traceability to our sort of best guess explicit mechanisms. So the common representative intermediate scheme kind of works from the other way around. It's much more of a top-down approach. So it takes a much more comprehensive model. In this case, it's the master chemical mechanism. And it has a very systematic way of simplifying that scheme to get it to a size that it can be fit into a 3D model through this iterative process of simplifying the intermediate steps that are taken in the chemical breakdown of VOCs, and then evaluating them against observations and chamber studies. And it goes through this cycle, and it means that you can always say that one version of the CRI mechanism is traceable to a particular version of the MCM, particularly when it comes to ozone production, which is very useful for the kind of science that we're interested in. So I took the CRI version 2.1, reduction 5, which is traceable to the MCM version 3.2. This is just a tropospheric scheme, so I also added the stratospheric chemistry that is in StratTrop. Overall, you have something which is over twice as complicated in terms of number of species and reactions. So you kind of see it as being an intermediate complexity scheme between something like StratTrop and a model such as MCM, which has got thousands of species and reactions. But it makes the model run 80% slower. So we're not necessarily saying this is going to replace the workhorse, but we do think that there's plausible that it can be used as sort of benchmark simulations. And it's committed and it's ready to use, actually, I think from 11.7. In terms of what chemistry this adds, these are sort of the key headlines. You've got C4 alkanes and or alkenes, aromatics, which are quite big in terms of anthropogenic emissions.
1 minute left, Scott.
1 minute, you say?
Mm-hmm.
Okay, and also like production of organic nitrates, and it also uses all of the VOC additions that are available, whereas StratTrop actually ignores quite a large proportion. So just some very quick highlights here. If you look at Alex's paper, there are some low biases in CO column. We actually do see quite a big increase in CO in CRI-Strat. This is due to secondary production from VOCs, particularly from biogenic regions. This is partly down to there probably being some high biases in biogenic emissions. But you do see a general increase across the world, and this could offset some of the biases in the high latitudes. This is actually dependent a lot on the emissions that CRI-Strat uses. So if CRI-Strat uses exactly the same emissions as StratTrop, you do see much less CO, and this has implications for the HOX and oxidant budgets. Likewise, if this is looking at NO2 column, we see these sort of quite big high biases from Alex's paper, particularly downwind of pollution sources. And in CRI-Strat, you actually see quite a big reduction in NO2. And again, this is sensitive to the VOC emissions that you have. What's happening here is that a lot of the NOx is reacting with those additional VOCs and forming reservoir species which can be transported away. And so you have this increase of NOx reservoirs, but a decrease of NOx near sources. So we can also say that something like NOx burden, if we see biases in NOx, it's not necessarily meaning that we have bias in the emissions, because we can also say that NOx burden is dependent on both the chemistry and the VOC emissions. So this is just general summary. I guess what we kind of want to say with this is this is a much more comprehensive scheme, and I think what for something like UKESM, I think an interest would be sort of benchmarking. So at the moment, we really don't know how much of these climate sensitivity and radiative forcing is sensitive to the chemical mechanism and what the implications that could be. But there's good reason to believe that it will be, given the changes to key components such as OX, NOx, CO, and HOX. This is committed in Ticket 4231, and there's a paper which will be published very soon on this. Thank you.
Yep.
Well, morning, everybody. I'm just I'm a PhD student working with Alex and Scott and Paul in Cambridge, and I've sort of put in a newer version of CRI-Strat, which is called CRI-Strat 2, with a lot of help from Scott and all these other people you can see down here, and also been looking at, as Gerd suggested, SOA and the SEC-Org scheme in UKCA. So very briefly, in terms of what CRI or CRI-Strat 2 does, it is very similar in many ways to CRI-Strat, and again, it traces its lineage back to the MCM version 3.3.1, so just a bit more updated. And the major feature is isoprene chemistry and the HOX recycling, which goes on there. So generally, we just get a greater amount of HOX in the biogenic regions. So at the bottom here, we can see a comparison of CRI-Strat 2 against StratTrop for the lowest sort of 500 meters or so, and we see particular increases in the isoprene rich regions of the tropics over Africa and the Amazon. The changes in the northern hemisphere are more due to changes in the NOx scheme, I believe. The top here, we see a comparison against observation. The black line is observation, and we've got the free mechanism, StratTrop in green, CRI-Strat, which is Scott's version in orange, and CRI-Strat 2 in red, and we can see an increase in OH, which is doing a better job, but still not perfect against observed OH from Borneo, the OP3 tower. So the bottom line is we get a better model performance in the tropical regions for isoprene, monoterpenes, and OH, and this can lead to a bit more of an assessment of, if we've got better chemistry, are these deficiencies now being caused by the emissions or uncertainty in the emissions? We're currently adding it to the trunk, so hopefully it will be there from version 12.1, 12.0, and we've got a paper looking at the gas phase impacts relative to StratTrop and CRI-Strat, which should be an ACPD very soon. Very quickly, then we've got some isoprene columns. These are the observations from Wells et al. and we see how the model bias decreases. It's high in StratTrop, particularly over the Amazon, and then it decreases to CRI-Strat, and then decreases again to CRI-Strat 2. This is all in the ACPD paper. In terms of the aerosol oxidant coupling, which I think is a really interesting area to look at, we plotted some two key sort of processes. We've got the oxidation of SO2 here, and it's very low altitude, only up to about 8 kilometers here. And we can see that in CRI-Strat 2, we see more oxidation in the boundary layer, and therefore less in the free troposphere. And we see a similar story with the SEC-Org production. Again, this is dominated over the tropics more, because this is Amazon and in Africa where we get the greatest amount of BVOC emissions. But bottom line is we are oxidizing more stuff very low down. So we expect SEC-Org to be more contained, i.e. less distributed, and that's going to have some interesting radiative effects. I should point out this bottom 2-panel plot is using the standard 26% monoterpene only SEC-Org production, so it has the problems that Gerd mentioned. So moving on, the other sort of piece of work which we've been looking at is trying to improve the SEC-Org scheme. So I have a development branch now where we've got 2 separate tracers, one for isoprene and one for monoterpene, and this should allow us much more flexibility in terms of boundary layer nucleation for some SEC-Org and not others. We can change the mass, we can change how things condense if we want to, and this can be broadened to looking at IEPOX, which is a major isoprene SOA component, but the pH is very important. So Steve Turnock's work may be really useful here. SOA from anthropogenic species, which is not included in CRI or StratTrop, so things like benzene and other LVOX. And then a long way down the line, not really, I guess, for UKESM2, but this is sort of what I'd like to look at later on, is a HOM scheme. So we've got a scheme which has CRI-Strat 2 with HOMs, and hope to put that into UKCA after my PhD. But this approach, which can be scaled up, can allow us to nucleate all sorts of stuff at different rates and explore the impact that might have, particularly on the pre-industrial atmosphere. So really, the science questions that we want to look at are the BVOC feedbacks on climate, and that's really what my PhD will finish on. And we're seeing some interesting things in terms of methane lifetime, and also how aerosols are dispersed with different oxidizing capacities, impacts of land use change, so things like deforestation. And finally, as I've shown already, the sulphate and the SOA differences are quite different in CRI-Strat and StratTrop, and there may be some interesting climate sensitivity studies that can be done there. Thank you.
So hello everyone. So I wanted to introduce you to the new scheme that we've been working on for quite a while, that include for comprehensive modeling of halogen chemistry in the atmosphere, which we call double extended Stratosphere-Troposphere scheme, abbreviated to DEST. And it's technically an extension of the standard StratTrop scheme, currently at version 11.0. And it includes many important updates to the halogen chemistry, and I'm going to glance through all of them for the next 5 minutes, hopefully. So first, as you know, the standard UKCA scheme lumps the contribution of most long-lived ozone-depleting substances into the 3 main ODS tracers. And here our DEST includes an explicit treatment of 13 long-lived ozone-depleting substances with additional 3 halogens lumped onto the 14th species. And this is something similar that was done in a very old CHES Plus version, but includes even more unlumped species. So secondly, DEST also includes biogenic emissions of 5 most important brominated, very short-lived species, including bromoform and dibromomethane. DEST also includes 4 most important chlorinated, very short-lived species, chloroform, dichloromethane, and the other 2 things. These can be imposed as either latitude-varying lower boundary conditions or as proper emissions. And we use both of those approaches recently for science runs, the results of which are currently being written up into papers. So this also includes phosgene chemistry. So phosgene, if you don't know, COCl2 is an important product of atmospheric degradation of both short-lived CLV-SLSs, but also some longer-lived ozone-depleting substances, CCCl4 and metal CCl3. And therefore, phosgene is important because it can act as a proxy for the emissions of those species. And there's also a bunch of other updates, including more halogenated tracers, updates to bimolecular reactions and photolysis reactions for the ozone-depleting substances. And we have also added more comprehensive wet and dry deposition of halogens. So we've done a fair bit of evaluation of this, which alongside the description of this is currently being written up and will hopefully be submitted to GMD in near future. And lastly, to say, we've been working on an extension of this that also incorporates iodine chemistry. So in particular, we've added emissions of some most important iodocarbons alongside a detailed iodine chemistry scheme, including 14 inorganic I species and also some new chemistry of iodine oxide. And we are currently in the process of testing it, so it's still like an active development. But just to say that Ryan has the funding to continue this development and will advertise a new PDR position shortly. So that's basically it.
Thanks, Luke.
Thanks, Paul. Can you hear me okay?
Yep, that's great.
Great. Can you see that?
I can see it in all its glory. Thank you.
Great. Thanks, Paul, for asking me to, or Paul Alex asked me to talk about this. I'm sure this is going to be a wonderful talk for everybody. So I'm going to talk about lodging code to the trunk. So I'll talk about the unified model development process and the kind of best practice associated with this, the testing that needs to be done in standalone suites. I'll talk about kind of the automatic tools that are used to kind of look at these as output from some of these suites, row stem, and then talk a bit about timelines and things like that at the end. So the unified model is almost 1 million lines of code. It's mainly in Fortran. There's a very particular set of coding standards that you will need to adhere to when developing code for the that you may not be used to using in your kind of usual kind of academic work. There are over 200 active developers at least, and it uses this ROSE graphical nameless editor, the Silk workflow engine, and code is held to version repositories managed using something called FCM. And you may need to, you'll certainly need to interface with FCM, and you will also may need to interface with this nameless editor to add new nameless entries and things like that. The process, there are 3 releases a year because the large number of developments going in mean that they don't want to have too few. They get very, very large otherwise. They're still very large. And the main thing is to start with is you make a ticket, you check out a branch from the trunk, you develop your code changes, you test them, you have a review process, and you commit things back to the trunk, and then you start the whole cycle again at the next version for the next release you want to do. The best practice, the first thing you should do is read the development working practices document. And this is on the front page of the Twiki. And it's very, very long and very detailed, and you probably won't need to think about all of it, but it's worth reading through and getting an idea because it gives you an overview of the whole process. It's really important to start early. You should begin developing your change as soon as you can. There are these kind of code freezes that occur regularly through the year. If you start developing a change just before a code freeze, it won't make it in for that next version. And so that will be wasting your time and potentially other people's time as well. So the best time to start is to start developing a change as soon as possible after the previous release. It's really important to talk to others. So Jane was mentioning this earlier as well. Talk to lots of people about the change that you're doing. If you've got a particularly big change, discuss it with me as the code owner to see how this fits with current plans. It may be that you need to tweak how you're implementing things a little bit. It's really helpful if you can find what's called the SciTech reviewer. So this is the person who kind of double checks that the change that you're making makes sense, who's familiar with the code area and the reasons for the change, and they'll be the one that approves. You need to talk to them about what plots and metrics they would like you to provide to demonstrate that your change works. As the code owner, I'm the kind of SciTech reviewer of last resort, but for people outside the Met Office, it may be beneficial to have somebody else, because when it comes to running row stem tests, I'm a person that can do those for you, and I can't do those tests if I'm also the SciTech reviewer. This is a plot from the working practices. I'm not going to talk through it in detail, but I recommend people look through it. You need to be aware of these blue sections here. So this update, ticket, committing and testing kind of cycle. And once you've got this done, you then kind of go through the review process. But like I say, I recommend reading the development working practices in detail to get an idea of the expectations and what you need to do. And there's, you know, there's actually quite a high minimum amount of time it takes, things you need to do, and you know, little fiddly bits you have to add on, and that's all covered in the working practices. Main thing is don't panic. These practices can be complex and difficult to engage with. They're all designed around working with a production code that's in use at the time for, you know, things like the weather forecast and important climate runs. You know, this code is updated, is run daily, updated regularly. If you need help and advice, I'm very happy to give it, as are many others who've been through this process. I think it's rewarding to get code on the trunk. And it's also, if you want it to be used by others more widely, you know, it kind of has to go on, really. You can't keep having branches hanging around. It gets very unsustainable. And then once code is on the trunk, it can then be considered for these science configurations. So like GA or UKESM, as Jane discussed earlier, you know, getting code on the trunk is the start of the process of getting it into a science configuration. It isn't the end. So you need to make sure that you get your code lodged as early as possible to allow enough time for scientific testing. If you're making science changes, you need to do some sort of test in a long simulation to show that the change that you're making is broadly doing what you intend it to be doing. You know, these don't have to be as detailed as the UKESM tests. It may be that you could do it at a UKESM test and that would be fine, and that would be a sufficient science test. This is separate from kind of development testing, which I'll talk about in a little bit. But generally speaking, a science change, you have to show on a kind of zeroth level that the code that you're doing, the code changes that you're making are doing what they're supposed to be doing. And they are kind of standard configurations that are provided that you can then run through tools which are called kind of auto-assess, Valno, and also the UKCA evaluation suite, which I'll cover in a little bit, and they produce plots for that you can kind of include on your ticket, and many cases those are the only plots you might need to include, rather than having to do lots of detailed plots of other things. Try not to make your code changes too big or too small. If you've got lots of little code changes, there's a big overhead associated with the ticket and with committing a ticket, and actually sometimes it's better to put similar changes together. So, but you don't want to make them too large, because the bigger a change is, it could have difficulty going through the review. It's much harder as a reviewer to kind of see the big picture in terms of a change. And so it's, you know, important to kind of try to find a sweet spot. Sometimes you can break things down to a couple of changes and then commit them over a couple of releases, and that's fine to do. All code changes must be tested using something called the row stem utility, which I'm going to talk about later. This isn't particularly difficult to use, and if you're coming from outside the Met Office, you may not be able to run it at all. And this is a kind of an automatic way of running standard tests of many different configurations, and these protect these existing configurations from accidental changes. And it's very easy to make an accidental change. You think that your code is fine, but you know, I broke the single column model once accidentally. You know, you need to these row stem tests to stop that sort of thing from happening. And conversely, if a configuration is not tested regularly, it's at a risk of breaking when something else is committed. So what is good to have happen is that, you know, with these new changes that are being committed, that a row stem test is also included. Otherwise, there's no guarantee that change will work at the next version beyond the one you're committing it into. And the key thing is you must be able to show that a change works when turned on. So these are kind of these science changes, and doesn't break anything when turned off. This is these kind of row stem changes, where break means change answers. And sometimes answers will be changed. If you're doing a kind of bug fix or something like that, it's fine. You know the answers are going to break, and you have to get approval from people to break it. The thing is that you might not be expecting answers to change, and that's when things get broken, and that's why the regular testing is useful. As well as your ticket and code changes, there are other changes you may need to make. You might need to make changes to documentation. So for kind of any new science options that are being added in, you'll need to document it in what's called the documentation paper for UKCA. And this kind of is a technical document that covers all the various options that can be made to UKCA. And if you've been on the UKCA training, you might have been given a copy of this. And you can see it on the list of DPs on the track pages. You might need to make changes to non-UKCA routines, and there you'll also need to interact with the code owner of those routines. You might need to make a new test in row stem if it's a big science change. You might need to just edit an existing test in row stem. So there is a kind of experimental UKCA test that's included, where you can turn your new changes on if they don't interact with other changes that are already turned on there. So that's kind of already provided for that. You may need to make changes to this, what's called rows metadata, and this metadata controls how the rows user interface looks and behaves. So if you're adding a new name list input, you've got to add it to that. You might also need to make changes to output or input, potentially, /master files. So you'll need to discuss these changes with the code owner of the sections affected, these reviewers of your code. So you'll have a SciTech reviewer, which kind of does the first review on the science change that you're making. And then there's a code system reviewer from the systems team, and that person kind of checks over the code, fits with the coding standards of the and is the person who eventually commits your code to the trunk. Owners of any row-stem configurations where you change the answers, other teams for like optimization, and other codes. You might be making JULES or Socrates changes for radiation. There are different testing suites. So, you might just be running a kind of global atmosphere run, which is just GLOMAP mode with offline oxidants, and there you'd run it through AutoAssess and ValNote. In UKCA, we provide two kind of testing suites. We've got a 20-year, year 2000 time slice for kind of StratTrop and CRI-Strat running, and you can also run a nudge configuration of this, and this is designed to be run with the evaluation suite. There's also a short 2-day suite. This runs some kind of row stem type tests, and it can run CRI-Strat as well as StratTrop and GLOMAP mode with offline oxidants. You may also need to test in ACRM suites if you also affect ACRM output. This is kind of what AutoAssess looks like. It compares your suite against a control. ValNote kind of compares your suite and the control suite against some observations or other model runs from later interim. And then the UKCA evaluation suite compares to other observational data sets. And often you can kind of run your control and your suite in both and then kind of put them side by side, as I've shown here. Note that with all these, the aerosol evaluation is poor. The IDL-based evaluation suite will no longer works because IDL isn't provided regularly to everybody anymore. And similarly, there's no aerosol assessment yet in AutoAssess. So with row stem, it tests 273 jobs from various architectures and compilers. It covers different types of tests, which I'll talk about in a little bit, and different levels of compiler settings. There are 28 UKCA jobs tested in row stem. And there's further tests for stuff like co-standards and metadata and stuff like that. This is kind of what row stem looks like. It goes through various different things. Some of these are what called known good output tests. So this checks, have you changed answers from before? Some of these are processor decomposition tests. So if you change the processors it runs on, do you change answers? Because you really shouldn't do that. Test number of OpenMP threads. If you change the number of OpenMP threads, it shouldn't change answers either. and it tests restart tests. So if you do 2 one-day jobs compared to 1 two-day job, do the answers change? Because again, the answer shouldn't change under those circumstances. And so all this is done for you kind of automatically. You want to run one line command, and it will send off, you know, load of jobs. It will click through them, and you get kind of all these failures come out in a table that you can add onto your ticket. So the first thing you do is you make a ticket, and then when you're ready for review, you kind of add things to this ticket. So output from these row stem tests, you know, links, auto assess, and evaluation suite output. Links to the code, documentation paper. You need to describe what the change is. You make a ticket summary, and you've got a load of questions you need to answer in the ticket summary. And these kind of short testing jobs provide the details you need to answer those questions, as well as the row stem test. You might need a ticket details page, which gives you further information, which provides further information on that. And then you pass it to your SciTech reviewer. Your reviewer will go over it, and if they're happy, they'll pass it to code system review, and if they're not happy, they'll pass it back to you with some questions. You need to make sure you respond to any questions and reviews before the ticket can go to the next stage. So I've just put an example here. This is actually committing the lightning notch changes Ashok was talking about earlier. And I'd suggest having a look at this and other tickets and get an idea for a feel of what you need to do. In terms of timescales, there's only about 2.5 months following one UM release before the next code freeze deadline. So this is the date by which the ticket needs to have passed to the code system reviewer, not for completing the review itself. That's done after that point. It takes time to prepare the ticket, do the code changes, do documentation. This minimum level of work can be quite high. If you're doing science runs, that might take 2 or 3 weeks to complete and then kind of assess. So, and it's easier if you don't break any row stem tests, but you know, you still probably have to do some science assessment, even if things are putting in on a switch. So plan for around a month of real time before you know, starting work, before your ticket goes to review, and then at least a week or so for turnaround there. And as I said, it's best not to start developing a change immediately. So it's best to start a change immediately following the UM release. Don't wait till the last minute. So for instance, the UM12 code review deadline is 21st of May. You know, ideally you should be starting pretty soon if you want to make that deadline. So my last slide, code development is complicated, can be seen as complicated and daunting, but the reason for this is because it's used by so many people and updated so frequently, and there are lots of checks to ensure that code doesn't break other things and is done in the best way possible. Things can still fall through the cracks though, you know, that this system isn't perfect. And you should start early with your development, talk to lots of other people, and I'm happy to help you through the process as much as I can. So get in contact if you want to know more. Thank you.